Okay, so this lecture focuses on proving NP-completeness of problems. Previously, we have shown that we can reduce satisfiability problem to a restricted version of satisfiability that we call the 3-SAT. So recall that in 3-SAT, we restrict each clause to contain exactly 3 literals. All right, and today we are going to show NP hardness or NP completeness of some other problems, and we'll talk about what's the difference again between NP hard and NP complete problems. And we'll start by establishing the fact that CLIQUE is NP complete. Okay, so first of all, let's state the CLIQUE problem. So recall that when we have an optimization version of the problem, we are trying to find the maximum clique, so the clique of the largest cardinality in the graph. Clique would be a decision version of this problem. So in this case, given a graph, and let's denote it by G with the set of vertices V and the set of edges E as usual, and an integer k, the question that we need to address is, does there exist a clique of cardinality at least k in the graph? Okay, so what we're gonna do, we will use the reduction from 3 satisfiability problem to CLIQUE to show that CLIQUE is NP complete. So here is our statement. So theorem CLIQUE is NP complete. And to show that any problem is NP-complete, usually we have to prove 2 facts about it. So first we need to show that the problem is in the class NP. CLIQUE belongs to NP. And this part is, so whenever a problem belongs to the class NP, in many cases it's actually easy to establish. And CLIQUE is one of these cases. So in this case, what we need to do is we need to provide a polynomial time verifiable certificate for a yes instance of the problem. So for example, if the answer is yes to the CLIQUE problem, meaning that there does exist a clique of cardinality at least k in the graph, all we need to do to prove this is to provide a clique on k vertices, and then it is very easy to verify that this is indeed a clique. So in this case, our certificate that we need to verify is any clique on k vertices. So once we find such a clique, right, so it's very easy to verify that this is indeed a clique by just looking at all possible pairs of vertices and making sure that they're connected by edges. So this takes at most order k squared time, and this is clearly polynomial, okay? So now, second, what we need to do in the second part is we need to find some known NP complete or NP hard problem that we can reduce to our problem. And in our case, we are going to use a polynomial time reduction from 3-SAT. So we'll claim that 3-SAT is polynomial time reducible to CLIQUE. All right, so for polynomial time reducibility, we need to provide a reduction from 3-SAT to CLIQUE. So given an instance of 3-SAT, what we need to do is to construct an instance of CLIQUE, and then, you know, we need to construct it in a way that by solving the CLIQUE problem, we can solve the 3-SAT problem. So, and 3-SAT problem would be some satisfiability formula with at most 3 literals per clause. All right, and look, for satisfiability, we have the input is given by these variables, right? Then we have the literals, and we have clauses, and we have a conjunction of clauses. Okay, so for an instance of the CLIQUE problem, we need to construct some graph in which we are looking for a CLIQUE. So how do we construct a graph based on this instance of satisfiability? So somehow we need to convert this input into 3-SAT, into an input for CLIQUE, right? So, and then what the correspondence could be. So let's consider the possibility. So with 3-SAT, so we have variables, then we have literals that correspond to the variables, or so literals would be a variable or its negation. So then we have clauses, right? So, and then clauses consist of at most 3 literals, not at most, but exactly 3 literals and 3 satisfiability. So which of these objects should be corresponding to vertices and edges in the graph that we are building? So somehow we need to find a construction where the cliques in the graph will correspond to satisfiability in the Boolean formula that we have. So let's say, let's look at some example for a satisfiability formula, for 3-SAT formula. So we could have something like this, x1 or x2 or negation of x3. And then the other clause could be not x1 or x2 or x3. So then let's put one more here. Okay. So now, looks like if we look at the clauses as vertices in our graph, then we can try to build something that corresponds to a CLIQUE. So let's try to construct a graph. So let's say this is your C1, the first clause. Then this is C2. And this is C3. So if you had vertices corresponding to clauses, then what would be the construction? So we need to have a CLIQUE in our graph that somehow corresponds to satisfying the formula. So nothing really crosses the mind, right? So, but then let's think about how do we satisfy the formula. So to satisfy the formula, we need to satisfy every single clause. All right, so there must be one of the, at least one of the literals here in each clause that actually gives you the true answer. Okay. So then for the formula to be satisfiable, every single clause needs to be satisfied. But look, when we look at 2 different clauses, you know, this may not be easy to satisfy them both at the same time. So we need to make sure essentially that satisfying 2 clauses at a time is compatible for every pair of clauses. So, and this is really our connection to the CLIQUE construction here, you know, because when we build a CLIQUE, we need to ensure that the CLIQUE consists of pairwise compatible vertices. We can call them compatible whenever they're adjacent to each other. All right, so this really gives a rise to a definition of vertices that we will have in our graph. So we'll construct a graph G with the set of vertices V and the set of edges E, where the vertices will be corresponding to these clauses. But then also, what's the connection between the clauses? This would be the literals that these clauses use. All right. So when can we satisfy two clauses at the same time? We need to make sure that assigning some of the variable to be, or some of the literal to be true in one of the clauses doesn't contradict to us assigning one of the literals to be true in the other clause. Okay, so then we can call them compatible or adjacent in our graph. So essentially, we need to take into account all the literals that we have in the clause. Okay, so then we can define the vertices as follows. So we can say that this is going to be the set of the following pairs. So we'll have CI on the one hand, so clause will be a part of the definition of the vertex, but then to this clause we'll have three vertices corresponding in our graph, and those three vertices would be let's say sigma ij. So this would be the literals that we have in this clause. And what are sigmas? So first of all, j goes between 1 and 3, right? So j is 1, 2, 3. And sigma ij is a literal. So it's a literal in the clause I, ci. All right. So this is how we define the vertices. Okay, so for example, for our formula that we have here, the vertices corresponding to the clause C1 would be the following. So it's going to be C1 and X1. So because X1 is the first literal in our clause, then we'll have C1, X2, and we'll have C1 not X3. Okay, so we have these three vertices corresponding to this first clause. And similarly, we'll have three vertices in our graph corresponding to each clause. So if we have m clauses, then we'll have three vertices for each clause. So it's going to be 3m vertices. Okay. So now, how do we connect these vertices by edges? So again, the edges are meant to represent the compatibility between the clauses. For each clause that we have, we don't have any edges between these three vertices. So this essentially will be an independent set on three vertices. But then for vertices between two clauses, we will actually need to figure out how we connect them. So essentially, to satisfy the clause 1, we need to make sure that at least one of these vertices gives you the true answer. So which means that either x1 is true, or x2 is true, or not x3 is true, meaning that x3 is false. All right, so and then when we assign these variables, so for example, if we assign x1 to true in the first clause, then we cannot satisfy the clause C2 by using the variable x1 anymore, because in the clause C2, we have the negation of variable x1. So therefore, we cannot satisfy C2 by this literal. So therefore, this two corresponding nodes in the graph will not be compatible, so meaning that we will not have an edge between these two. On the other hand, if I look at, let's say, C1x2 versus C2x2, so we can satisfy these both clauses by setting the variable x2 to true. So, which means that now these two vertices will be adjacent in our graph. Okay, so they can two belong together to this clique. Okay, so let's illustrate this in more detail in the next slide here. Okay, so we had let's see, so we had x1, x2, and not x3. So let me draw again these nodes for the first clause. So then we have C1, x2, C1, not x3. Yeah, so we have these three vertices for the first clause. Then for the second clause, we have the vertices C2, not x1, C2, x2, and C2, x3. So how are we going to build the edges? Whenever the node from one layer, so and we have these different layers corresponding to the different clauses, whenever a node from one layer can be used to satisfy the corresponding clause, and a node from another layer can be used to satisfy the respective clause as well, and these two don't contradict to each other, we have an edge in the graph. So essentially, whenever the literal in one layer is not a negation of the literal in the node of the other layer. So let's say for x1 and not x1, obviously we don't connect them. These two are compatible, right? So then, because I could satisfy the first clause by setting x1 to true and the second clause by setting x2 to true at the same time, then these are compatible as well. All right, so then x2 has no conflicts with any nodes here. And for this one, we'll have two neighbors in the layer corresponding to the second clause. Okay, so then let's draw the third one. So in the third one, we have the negations of all the variables. So we'll have C3 not x1, C3 not x2, C3 not x3. And looking at the compatibility, so first with the first clause. So again, C3, C1 x1 and C3 not x1 are not compatible, but C3 x1 is compatible with C1 x2, and it is compatible with this one as well. Okay. So then let's look at the second one. C1 x1 and C3 not x2 is okay. Okay, let's see. Then C1 x2 and C3 not x2, we cannot have x2 and not x2 true at the same time. So no edge there, but we have this edge right here. And finally, for C3, it's connected to the first one here. The second one and the third one. So we have all three edges for this one. So then finally, between the second and the third clauses, so we have all compatibilities here. Then for not x2 in the clause C3, it's compatible to 2 of this. And then for not x3, we also have 2 neighbors here. Okay, so this is our construction now. So essentially, the way we built the set of edges, it was the following. So E was the set of the following elements. So it would be the set of CIs. Let's see. We use the figure brackets to represent the edges here. So it would be CI sigma ij or in fact, I don't really need to specify here i's and j's, so let's keep it simpler. So I can just say ci sigma, so that's one vertex, so, and obviously this sigma must be one of the literals from the clause ci, by the way we define the vertices. And then the other vertex will be the jth clause, and let's call this sigma prime here. And when do we connect them by an edge? Is when sigma is not equal to not sigma prime. So this is how we define the edges, right? So the only way we don't have an edge is when setting one of the literals to true contradicts to setting the other literal to true. Okay, so now whenever we have an edge between the two vertices here, this means that we can use the corresponding literals to satisfy the clauses that these vertices represent. And clearly, you don't have the edges corresponding to vertices from the same layer corresponding to the same clause, right? So essentially, this graph is a multi-partite graph. So we have each part consisting of an independent set with 3 vertices. So and how many parts we have? So we have as many parts as there are clauses in the 3-SAT formula. So we have m clauses, so this is an m-partite graph. So now imagine we have a clique in this graph. If we have a clique in this graph, it means that we manage to satisfy essentially every clause at the same time, right? So because there is no contradiction between any pair of assignments for the literals. So and clearly, once I find a clique in this graph, all I need to do, I just need to set all the literals corresponding to vertices in this clique to true, and this will mean that we will satisfy the 3-SAT formula. All right. So essentially, we can claim that G has a clique of cardinality M if and only if the formula F is satisfiable. And then the proof, again, is pretty straightforward. So if I have a satisfiable formula F, so then take the assignment of the variables that makes the answer yes or true, and then pick the corresponding vertices to be in the clique. And clearly, because we were able to set all these literals to true at the same time, there are no incompatibilities there, so you have a clique in the graph, right? So it's going to be of cardinality M because we pick exactly one vertex from each level here, all right? And then, if you have a clique of size m in the graph, then by setting all the literals corresponding to the vertices in the clique to true, we satisfy the formula f. So it goes both ways. And from here, we have a polynomial time reduction. This shows that clique is NP-hard. So this second part essentially shows that clique is NP-hard. Because we had the polynomial time reduction from three-sat problem, which is known to be NP-complete. And together with the fact that clique belongs to the class NP, so which was the first part of our proof, we conclude that clique is NP-complete. Okay, so once again, to show NP-completeness, we need both of these parts. NP-hardness only requires the second part. All right, so what is NP-complete? This is an NP-hard problem that also belongs to class NP, and clearly clique belongs to class NP, so therefore we have NP-completeness for the clique problem, okay? So this completes the proof. So, and now, remember that we said that a subset of vertices is a clique in G if and only if this subset of vertices is a clique, is an independent set in the complement graph. So also we said that this is the case if and only if the vertices outside of the independent set are going to give you a minimum vertex cover or a vertex cover in the complement graph. So V minus C is a vertex cover in the complement graph. So which, these relationships give you straightforward reductions from the clique problem to the independent set problem and the vertex cover problem. All right. So therefore, we can claim in the same way that the independent set, so as a corollary of this, we can claim that independent set so C, independent set would be the decision version of the maximum independent set problem, which given a graph and some integer k asks if the graph contains an independent set with at least k vertices. So similarly, vertex cover, this capitalized spelling and without saying minimum. So vertex cover problem would be given a graph and an integer k, does there exist a vertex cover in the graph with at most k vertices in this case? So this is a minimization problem, right? So these two decision problems are NP-complete because we can easily reduce clique to these two problems. All right. Now, if we go back to optimization version of this problem, such as maximum clique or maximum independent set and minimum vertex cover, we can claim that these problems are NP-hard because we can show that clique, for example, reduces to maximum clique in a straightforward fashion, right? So how does clique reduce to the maximum clique? So essentially, I need to solve the clique problem by solving the maximum clique problem which is kind of straightforward, right? So if I solve the maximum clique problem, then I know exactly the size of the maximum clique in the graph. So, and then depending on whether this size of the maximum clique is greater or less than k, I can have the answer to the question asked in the clique problem in a straightforward fashion, right? So we can claim that maximum clique problem is NP-hard, and similarly, maximum independent set problem and the minimum vertex cover problem are all NP-hard. They're NP-hard, but again, we cannot claim NP-completeness. So let me state this here formally. The maximum clique maximum independent set problem and minimum vertex cover are NP-hard, but not NP-complete, okay? Why are they not NP-complete? Because they don't belong to the class NP. They're not in NP because the class NP consists of the problems that can be answered by either yes or no, and clearly these optimization problems cannot be answered by one of the two simple answers, right? Okay. So now we proved the NP completeness of several more problems. So see, we are increasing the arsenal of the problems that we can use for reductions for other problems to show that other problems are NP-hard or NP-complete. All right, so, and I want to state next a general result by Yanakakis that actually allows to establish NP-completeness by applying this theorem or NP-hardness by applying this theorem in a straightforward fashion. So it applies to many different problems. So to state Yanakakis' theorem, we need to introduce some new definitions. So in particular, we'll need the concept of heredity property in the induced subgraph, okay? So heredity in the induced subgraphs. So this is for graph properties, or to be more specific, for properties satisfied by subsets of vertices. So, and you know, as a working example, that let's actually use the property of a subset of vertices to be a clique. All right. So this is one of these properties that satisfies the heredity property. So we say that a property pi so we are talking about some graph property pi of a subset of vertices is hereditary in induced subgraphs if so if I have a subset of vertices C that satisfies the property pi, then for any subset of vertices let's call it C prime, that's a subset of C. C prime will also satisfy pi. So it's hereditary in the induced subgraph. So essentially, when we say that C satisfies this property, it means that some property in the subgraph induced by G of C, by C, that would denote by G of C, will be satisfied. So, and then what's the induced subgraph? So I'm not sure we defined this concept before. But essentially, if you have a graph, some arbitrary graph, and the subset of vertices in this graph. So let's look at some arbitrary example here. So then let's say if I decide to pick some subset of vertices that I will put in red here. So let's say these three vertices will be my subset that I'm considering, and then the subset induces a subgraph. The induced subgraph will consist of these three vertices, and it will consist of only the edges in between these vertices, and we essentially ignore all the edges that have at least one endpoint outside of the set. Okay, so this is the induced subgraph. When we just simply say a subgraph, we could actually drop some of these edges. So let me maybe formally state here the difference between subgraphs and induced subgraphs. So G prime would be a subgraph of G. In fact, let's denote by V prime and E prime the set of vertices and edges of G prime. If V prime is a subset of V and E prime is a subset of E. So, but for the induced subgraph, so for a subset of vertices, let's call it C, the induced subgraph as we denote by G of C with the square brackets. So it has essentially C as the set of vertices and the intersection of E with the edges from C that we denote by C choose 2 would be essentially pairwise, pairs of vertices from C. So this is your set of edges, right? So essentially, once both of the vertices are included in C and they have an edge between them in G, that edge must be transferred over to the induced subgraph. And this doesn't have to be the case when the graph is just a subgraph, but not an induced subgraph. So anyway, we stated this heredity property in the induced subgraph. So property pi is hereditary in the induced subgraphs if the fact that some subset of vertices satisfies this property means that every subset of this set C also satisfies the property. So for example, CLIQUE is a hereditary property, because if I have a clique in a graph, then any part of the clique is also a clique. An independent set is a hereditary property because, again, any subset of an independent set is also an independent set. All right, so, and then we'll define a couple of other properties for graphs, which essentially hold for any problems that we are interested in. So we'll say that a property is non-trivial. So a graph property pi is non-trivial if it is satisfied by a single vertex so essentially this would be a single vertex, which is a part of V, of course, but not satisfied by every subset of vertices. So by every subset of vertices for every graph. So essentially, it tells you that what the name says, it's non-trivial, right? So if it was satisfied by every graph and every subset of vertices, so then the property would be trivial and not interesting from an optimization perspective. So then, but we also have another concept of an interesting property. So pi is interesting if there are arbitrarily large graphs that satisfy this property, essentially. So arbitrarily large G such that V satisfies P, pi. Okay. So essentially, if the property was only satisfied for a certain size of the graphs, then again it wouldn't be interesting from an optimization perspective because we could solve it in constant time, right? So if, let's say, if it was satisfied only for graphs with 100 vertices or less, or something like this, right? So you could enumerate all the possibilities in a constant time, and it wouldn't be interesting from an optimization perspective. But clearly we can come up with, for example, a clique or an independent set of arbitrarily large cardinality. So obviously these two graph properties are interesting according to this definition. So and they're non-trivial and interesting. But you see, these properties of being non-trivial and interesting is something that is pretty much a given in many of these problems that we are considering. So therefore, we kind of expect to have these properties in many problems, and they're trivial to verify. Now, heredity is also a property that is very easy to verify, but it's not satisfied by as many problems or as many properties as non-trivial and interesting properties are satisfied by. Okay, so now Yannakakis theorem that we state next. So this was proved by Yannakakis in 1978. So it's a nice and pretty general result that tells you that the problem of finding a maximum cardinality subset of vertices that satisfies a property pi a given property pi which is non-trivial then interesting and hereditary in the induced subgraph. So we have these three properties, right? Of course, the key of which is hereditary in the induced subgraph is NP hard. Okay, so this theorem provides a pretty powerful tool for establishing the NP hardness of many problems that satisfy the hereditary property. So, for example, some of these problems that I gave you in the homework, actually, I suggested to go over the homework problems and see which of the problems that I ask you to formulate actually satisfy the hereditary property. All right. So, but again, each of these three properties is really easy to verify. And once you know that these three properties are satisfied, this is sufficient to establish the NP hardness. All right, so next we are going to establish the complexity of one more classical optimization problem in graphs. It's called the minimum dominating set problem. So let's first define the dominating set. So a subset of vertices is a dominating set. So let's call it D. A subset of V is a dominating set. If essentially every vertex in the graph is either a part of this set or has at least one neighbor in the set. So if for any I in V, we have either one I is in D or two there exists another vertex in the set D such that the edge ij is in the graph. Okay, so now, of course, the minimum dominating set problem would look for a dominating set of the smallest cardinality. And this is a classical problem, so it has applications in, for example, sensor placement. So you want to place a minimum number of sensors such that you can survey the whole network. And then the decision version of this problem, we'll call it dominating set. So it's going to be given a graph G and an integer K. You need to answer the question, does there exist a dominating set of cardinality at most K in G? So then we'll show that the dominating set problem is NP complete. So let's call it DS is NP complete. So for the proof, again, we'll have two parts. The first part will be DS belongs to the class NP. And this, again, is straightforward because once we have a dominating set with K or less vertices, we can use it as a certificate for any yes instance of the problem. And clearly, it is easy to verify that the dominating set is indeed the dominating set. So it's clearly polynomial. So dominating set is in the class NP. And then the second part, we will reduce the vertex cover, which we already know is NP complete, to the dominating set problem. So the vertex cover is polynomial time reducible to dominating set. And the construction is actually not difficult to come up with. So let's say, given an instance of vertex cover, so you have G is an instance of vertex cover. So we need to construct an instance of dominating set such that there is a correspondence between dominating set in this instance and the vertex cover in the graph G. Okay, so we can construct the following instance. So construct an instance G bar with the set of vertices G prime, V prime, E prime of dominating set as follows. So essentially in vertex cover, we are looking for the smallest subset of vertices that will dominate edges in a way, right? So what we need to do, we need to come up with the set of vertices in the instance of the dominating set where the original set of vertices, so let's say if you look at the set V and say I consider the vertex I and the vertex J, if they form an edge in the original graph G, then in this new graph G prime, we are going to include a vertex corresponding to this edge in the set of vertices V prime. So essentially for the vertex IJ in this new graph G prime, so this vertex in the new graph, it used to be the edge in our graph G, right? So, and we connect both vertices I and J to this new super vertex IJ that corresponds to the edge in graph G. And essentially, we can think of the vertex cover problem as a dominating set problem in this expanded graph, right? So V prime here now is going to consist of a union of V and E. So because, look, we have a vertex in G prime that corresponds to every edge in addition to the vertices of the graph G. And we are looking here for a dominating set. And we need to show that a dominating set in G prime will correspond to a vertex cover in the graph G. So let's first define this set E prime. So E prime is going to be the set of edges in the following form. So we'll have I and let's call it K, let's say, will be the vertex that corresponds to an edge in the graph G, such that, actually, let me maybe to be more precise, instead of K, I'm going to use E here, sorry. So it's going to be I, E. So for the edge where let's see. So we have I is in E, in V, and edge E is equal to some ij in the set E. So essentially, we have the edges correspond, so these edges in the graph G prime, they correspond to the pairs of vertices such that one of the vertices is a vertex in the original graph, and the other vertex is the edge in the original graph that contains this vertex I, okay? All right, so we have this construction, but let's see if it really gives us exactly what we need. So let's say if my graph G consists of just one edge ij, and then G prime will just be these three vertices. So then what is going to happen, my minimum dominating set in graph G prime will consist of a single vertex that corresponds to the edge ij in graph G. And then, how do I convert it into a vertex cover containing just one vertex in graph G? So it becomes a problem, right? So we need somehow to ensure that any dominating set, any minimum dominating set in graph G prime corresponds to a vertex cover we want it to be the same size in graph G. So it may make sense to add actually all the original edges that we had in graph G to the set of edges in graph G prime. So let's say if ij were connected by an edge in G, we are still going to connect it here. All right. So then we'll have to combine it with essentially E prime will contain these new edges that we added, plus it will still contain the edges from the set E. So maybe let me put it the line above. So yeah, let's keep the original edges between the vertices from the set E, and we combine it with the new edges between these two parts right here. Okay. So now, if let's say we find a dominating set of size K in the graph G prime, and if this dominating set contains only the vertices from the set V and no vertices from the set E, then this dominating set in graph G prime will be exactly a vertex cover of size K in the original graph G. right? So because for this set to be dominating, it must all the nodes from the set E in graph G prime must be dominated by vertices from the set V, and this exactly corresponds to the vertex cover in graph G. On the other hand, if, let's say, our dominating set of size k in graph G prime contains a vertex from the set E, then what we can do, we can just replace that vertex of the vertex that from the set E with either I or J. And then clearly, you know, any vertex from the set E, so this vertex can dominate only two vertices, which are I and J, because it's adjacent to only two vertices in the graph G prime. So clearly, by replacing this vertex with either I or J, the set will still remain dominating in graph G prime. And therefore, this way we can replace every vertex from the set E in the dominating set in G prime with a vertex from the set V. So, and then as a result, we are going to convert any dominating set of size k from graph G prime to an alternative dominating set of size k from G prime, which will only include vertices from V. And then once you have a dominating set in G prime that contains only vertices from V, that dominating set in G prime is clearly a vertex cover in the graph G. So, and therefore, we can claim that G prime has a dominating set of cardinality k if and only if G has a vertex cover of cardinality k. So therefore, now we have the reduction from vertex cover to dominating set, so which means the dominating set is NP hard, and together with this first fact that dominating set belongs to the class NP, we can claim that dominating set is NP complete. So the proof is done. Okay, so the last complexity result that I wanted to discuss is inapproximability of the k-center problem. Okay. So let's recall what the k-center problem is about. So essentially, you have n different potential locations for the center. So let's call this, let's say, the set V, 1, 2 through n potential center locations. So, and then let's denote by Aij the distance between locations I and J. So imagine the situation that these different potential locations are, say, different villages, right? And then you want to build k hospitals that are going to serve these n different locations. So you want to decide in which villages you're going to build the hospitals. So we want to build K centers, and then the problem is, the K center problem is to open these K centers in a way that the longest distance from any location to the closest center is as small as possible. So essentially, no village is too far away from the closest hospital. All right. Determine K center locations such that the longest distance from any location to the closest center is as small as possible. Okay. So in addition to this, we assume that these distances here satisfy the triangle inequality. So assume that aij's satisfy the triangle inequalities. So which means that, let's say if I have 3 different locations, so let's say I, J, P are the 3 locations. So then aij, so going from I to J directly is going to be no longer than going from I to P first, and then from P to J. Okay, so these are pretty much a very reasonable assumption, right? It's practical in many cases. So, and we are looking at the restricted version of this problem, so which means that by enforcing this assumption that the distances satisfy the triangle inequality, we could say that we are making the problem easier than the general problem. So because you cannot have like crazy distribution for the distances, and it's more or less realistic and supposed to be easier to deal with. Okay. So nevertheless, we will show that it is actually NP hard to find the problem of approximating this K-center problem within the approximation ratio of 2 is NP hard actually. Okay, so we are going to look at the problem of approximating this. So we want to find the approximation algorithm. So to find an approximation algorithm for the K-center problem. So the approximation ratio would be, let's say, R, right? So essentially, if I want to say that let R be the approximation ratio, so then what is our approximation algorithm? So let's say denote by CA the optimal objective value, the objective value obtained using the approximation algorithm A, right? So let's say quality of the solution obtained using algorithm A, which will be our approximation algorithm. So then let's denote by C the optimal solution value. Then our approximation algorithm would be trying to find an algorithm that guarantees that CA is going to be less than or equal to R times C star. All right, so we're going to show that finding a two approximate solution. So for R equal to 2, the problem is already hard. Okay, so finding, or wait, sorry, 2 minus epsilon. So finding approximation ratio better than 2 is going to be hard. So we can actually find the 2 approximation algorithm in polynomial time, but 2 minus epsilon is going to be hard. Okay, so we will show that finding a 2 minus epsilon approximate solution so for K center is an NP-hard problem, actually. Then we can claim, actually, once we prove this, we can claim that the best you can hope for to solve in polynomial time, the best approximation algorithm in terms of the approximation ratio that you can guarantee in polynomial time would be a 2 approximation algorithm, because this result is actually, so here for any epsilon greater than 0, okay, so even if it is like 0.00001 or anything better than 2 is hard to guarantee. Okay, so let's see how we show something of this sort. Okay, so proof for this. So what we're gonna do, we will reduce dominating set problem, so reduction from dominating set problem. So, and in fact, when we say here that finding 2 minus epsilon approximation for K center is an NP-hard problem. So we are talking about a restricted case when the distances satisfy the triangular inequality. So remember that we have this assumption here. So we assumed that the distances satisfy the triangular inequality. So this result holds even for this restricted case, which is supposed to be easier than the general case, right? So the reduction from the dominating set is as follows. So what we're gonna do, we will construct an instance, given an instance of a dominating set problem, so let's say we have this graph G VE of DS, we construct an instance of K-center as follows. So with distances satisfying the triangular inequalities, so okay, so we have the same set of locations. So essentially, the locations, the set of locations will be given by V. So the vertices will be our locations, right? So and then Aij will be defined as follows. So you have Aij will be depending on whether you have an edge in the original graph, in graph G between I and J. So if you have an edge, then you will say that they're close to each other, so the distance is going to be 1. 1 if Ij is in the set E. And then if they're not directly connected by an edge in E, then we'll say that the distance is 2. 2 if Ij is not in E. Okay. So then let's see what is the correspondence between the K-center solution and the dominating set solution. So look, so first of all, these distances satisfy the triangle inequalities, right? So because if I consider any 3 vertices, let's say, so you have I, J, P. So then you have what are the distances. So for each 3 of these, depending on whether these locations were connected by an edge in the original graph G, so each distance is going to be either 1 or 2, right? So, and no matter how you assign the distances, so let's say, you know, consider any possibility. So let's say 1, 1, 2. So the triangle inequalities will clearly be satisfied, right? So whatever combinations of 1 and 2 you consider, the triangle inequality will be satisfied. Okay. So now another property is for this K-center problem is C star is either 1 or 2. So 1 or 2 are the only possibilities for the optimal solution for the K-center problem. So because look, the objective of the K-center problem always corresponds to one of the distances between the locations. So because our distances are limited to either 1 or 2, so the optimal solution must be either 1 or 2, right? So, and in fact, you pick any combination of K centers, so pick any arbitrary K vertices or K locations to be your centers, and the solution is guaranteed to be no worse than 2. Okay, so every, again, you know, every set of K locations will give you the objective that's no worse than 2. So, but when is the objective of 1 possible? Only when this set of locations that you pick for the centers will form a dominating set in the original graph. So it's very easy to see that this will be the case. So the optimal objective will be equal to 1 if the K centers, if essentially there is a dominating set of size at most K in the graph G. If there exists a dominating set D with the size D no more than K in G. So, but then if none exists, then you cannot pick the set of K centers that will ensure that every other center essentially has a distance no more than 1 to the closest center. Okay, so we have this nice correspondence between the instances. Moreover, so assume I have a 2 minus epsilon approximation algorithm. So if we had the polynomial time a 2 minus epsilon approximation algorithm, for our instance of the K-center problem, then what would this mean? So this would mean that whenever my graph G has a dominating set of no more than K vertices, this approximation algorithm, so what does 2 minus epsilon approximation algorithm mean? So whenever I have a solution, whenever the optimal solution for my K-center problem has the objective of 1, this 2 minus epsilon approximation algorithm is supposed to find a solution which is better than 2 minus epsilon. So, but because our objective can only be either 1 or 2, if it is better than 2 minus epsilon, then it has to be 1, right? So then this essentially is an exact algorithm for our K-center problem. So this algorithm would be exact for our instance of the K-center problem. So now what does it mean? That this means that you would have a polynomial time algorithm for the dominating set problem solves the dominating set problem so therefore we reduce the dominating set problem to this the problem of approximating the K-center with the approximation ratio of 2 minus epsilon, so which means that essentially the K-center problem is NP hard to approximate within the approximation ratio of 2 minus epsilon for any positive epsilon. So this is an example of how we can prove inapproximability for certain problems. So essentially we create this gap here between the possible objective values. So like in this case, it's going to be either 1 or 2, right? So, and once you have better than 2, you have to have 1. So an approximation algorithm essentially with a ratio better than 2 is equivalent to an exact algorithm for this problem. So in this way, we prove inapproximability result.